Okay, so we're in section 3-1 of the differential equation book, and the issue is series expansion. And as you may or may not recall, there's a Taylor expansion, and Taylor expansion, and we're going to go around a is equal to 0 to make it easy on ourselves. And it says if I have a function f of x, then the expansion of that function is going to be f at 0 divided by 0 factorial plus f prime at 0 divided by 1 factorial plus f double prime at 0 divided by 2 factorial plus blah 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 plus f the nth derivative at 0 divided by n factorial plus blah 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 forever and ever. So that's the Taylor expansion around a is equal to 0. If I'm not going to do it around 0 because at 0 I have a singularity or something, I have to change the expansion to be around 1, then it's going to be something different. So if I do it around a is equal to 1, for example, then f of a minus 1 would be f at 1 divided by 1 factorial, 0 factorial plus blah 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 plus the nth derivative f at 1 divided by n factorial. And with a little bit of luck we won't have to deal with that, so it won't be too much of a problem. Now if I look at that I say, well, why don't we take something like e to the x? So f of x is equal to e to the x, and f at 0 is 1. And f prime of e to the x is e to the x, and f prime at 0 is 1. You see a pattern there? So if y is equal to e to the x, then its series expansion is going to be 1 plus x squared over 2 plus x cubed over 3 factorial plus x4 over 4 factorial plus blah 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 x to the n over n factorial blah blah blah. Or I could say summation n equals 0 to infinity x to the n over n factorial. I could write it that way as my series expansion of e to the x. I can do the same thing with cosine. So if y were cosine x, y at 0 would be 1, y prime would be minus sine x, y prime at 0 would be 0, y double prime x would be minus cosine, and y double prime at 0 would be minus 1, y triple prime at 0 is going to be 0, and then I'm going to run back and get on top of it, do it all over again, and the fourth derivative is going to be 1 because I'm a repeating guy. So the expansion of cosine is going to be 1 minus x squared over 2 factorial, which is the same thing as 2, plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Now, when you were discussing sines and cosine, you said that cosine was an even function, right? You remember that? Cosine is an even function. Well, if I look at the series expansion of cosine, I'm even. All those exponents are even. So the cosine of x is equal to the cosine of minus x, and that's the definition of an even function. If I do the same thing with sine, I end up with sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And I end up saying that this is an odd function. We say the sign is odd, and I look over there and I have all odd exponents. I most certainly do. And then we say, well, you know, the derivative of the sine is cosine, right? So I take the derivative of this thing, and what do I get? Oh wow, I get the series expansion of the cosine function. So now I have a continuous thing going on. Now I've got hyperbolic sine, hyperbolic cosine. Why not? Hyperbolic sine x, hyperbolic cosine x. And I end up with 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus blah, 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 blah. And hyperbolic cosine, I end up with x plus x cubed over 3 factorial plus x to the 5th over 5 factorial. And when I take the derivative of the sine, I'm supposed to get the cosine, hyperbolic cosine. And we take the derivative of hyperbolic cosine, I'm supposed to get the hyperbolic sine, and I do. Okay, so all those are relatively important things. So now we're going to consider, well, I have some function y. It will have a series expansion, and it's going to look like 0 to infinity a n x to the n. So I'm not committing on what the coefficients are. I'm just saying it exists. So in that case, it does. It just exists. And then I said, well, if my function y is in that form, then what does y prime look like? Well, y prime is going to look like n equal 1 to infinity n a n x to the n minus 1. So I take the n, put it out in front, subtract 1 from it, and then I look at the second derivative and I say, well, that's going to look like n equal 2 to infinity n minus 1 a n x to the n minus 1. And now we have a method to use this series expansion to find the solution to a differential equation. So we'll try to do that. Let's see. So y minus y prime minus y is equal to 0. So we have a characteristic equation, m minus 1 is 0, m is equal to 1, y is equal to e to the x, right? So that would be c1 e to the x. All right, so now we know the answer to that particular guy, right? And now we're going to go and say, well, y is equal to summation n 0 to infinity a n x to the n, and y prime summation n equal 1 to infinity of n a n x to the n. And then we're going to go and say, well, y prime minus y is 0. What does that mean? Well, that means that summation n equal 1 to infinity n a n x to the n minus summation n equals 0 to infinity of a n x to the n is going to be 0. Okay, so I look at that and say, well, look at this. I have an index starting at 1, and I have an index starting at 0. I'd sort of like to put this all in one summation. So I'm going to do a substitution, and I'm going to say n is equal to n plus 1. I'm going to do that substitution in the first guy. So when I do that, I'm going to have summation n equals 0 to infinity, n plus 1, a n plus 1, x to the n plus 1. Well, no, I don't, because this is n minus 1, and that's just going to be a to the n, minus summation n equal to 0 to infinity a n x to the n is equal to 0. And now I can put it all underneath the same summation sign. Summation n equals 0 to infinity, and I have n plus 1, a n plus 1 minus a n x to the n is equal to 0. Okay, so now I've got that. Now, if I have something that's, let's say I've got 2 plus x plus 4x squared plus 3x cubed plus 7x to this fourth plus, and I go all the way out to infinity, raising my powers every time I go. And I say that's equal to 0. What do we know? Is there anything that we know? Well, we know that these guys are linearly independent of each other, right? So how in the world are they going to be equal to 0? So we're going to erase that for a moment, and we're going to consider this guy right here. If each of these terms is linearly independent of each other, because there's a unit term, an x term, an x squared, they can't be multiples of each other. The only way this summation can be 0 is if the coefficient in front of those x terms is 0. So we have a thing we call a recurring formula, and it says that this n plus 1 times a n plus 1 minus a n has to be 0, because x to the n isn't going to be 0. That wouldn't make any sense. That'd be trivial. So that being the case, I can have that a n plus 1 is equal to a n divided by n plus 1. Okay, that's fine. What's a0? What's a0? So I have y is equal to a0 plus a1x plus a2x squared plus a3x cubed plus blah, blah, blah. What's a0? Y at 0 is a0. That's an initial condition, right? What do we know about an initial condition? I don't know what it is unless you tell me, right? Okay. All right. Well, we'll go with that. All right. So what we're going to do is say a0 is arbitrary. Okay. Well, if a0 is arbitrary, what's a1? a1 is a0 divided by 1. What's a2? Well, a2 is going to be a1 divided by 2, which is going to be a0 divided by 2. And what's a3? a3 is going to be a0 divided by 2 divided by 3. a0 divided by 3 factorial. What's an? an is going to be a0 over n factorial. So y is going to be a0 plus a0x plus a0 over 2x squared plus a0 over 3 factorial x cubed, blah, 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 a0 over n factorial x to the n, going out to infinity now. What's that? Well, that's a0 times 1 plus x squared over 2 plus x cubed over 3 factorial plus blah, 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 x to the n over n factorial out to infinity, a0 e to the x. That's exactly what we said the original solution was going to be. We said it was going to be a0, some constant of integration, times e to the x. So we're going to use this method to solve differential. Now clearly, to use it to solve that differential equation would be something you'd put on a test so you'd have a chance to get it right, right? That'd be the only reason you'd use it in that case. You have so many better methods to get to the solution than filling up a whole sheet of paper. But there are other differential equations that we have to do with a series approximation because we have no other choice. And so that's what that's all about. Okay, so we did that. We considered that. Okay. Now we're going to consider for a moment a series approximation may converge or it may diverge. So if I have 1 plus a half plus a quarter plus an eighth plus a 16th plus a 32nd plus blah blah blah, that guy's diverging, that guy's converging, and he's heading towards 2. But if I had a 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus blah 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 blah, he's diverging. He is never, he's just getting bigger and bigger and bigger, and we're never going to get to a single spot. Do you believe that? Why not? I told you that. What more do you want? There's a 1, right? Bigger or less than 1? Bigger than 1, right? Bigger than 1? The next 5 guys over, bigger or less than 1? Bigger than 1, right? The next 7 guys over, the next whatever guys over. So I'm always getting something bigger than 1 when I group these guys up. And even if I'm out I'm dividing by 100, 1 over 100,000 plus 1 over 100,000 plus 1, I can find a group of them to be bigger than 1. Yeah, so I'm not getting smaller. I'm not. So that guy is diverging. So I have a rule. I have a rule that says, it's a radius rule, R-A-D-I-U-S. And it says that if I look at, if I have some c n x to the n guy, and I look at the limit as n goes to infinity of cn over cn plus 1. And I look at it as an absolute value because this could be doing a plus and minus thing. And if I look at that and I see that this r is equal to 0, then the series is going to diverge. And if the r is, if 0 is less than the r is less than infinity, then the series is going to converge as long as the absolute value of x is less than p, and diverge if the absolute value of x is greater than p. And if p is infinity, then it's going to converge for all x's. So I have some test that tells me. So I could go to Maple and I could bring up a differential equation, and the analog solution could look something like this. I got some solution that looks like that, analog solution. The series approximation is going to look like this, and then it's going to start doing things like that. It's gonna because when I take x to the 50th of some number, I'm going to start getting huge spikes going back and forth in that series approximation that I can't control. So my series approximation might be perfectly okay out to 10, but if I go to 12, I'm going to diverge, and I won't have a series approximation. So it might be that could happen to me. Okay. So now we're going to work on some problems. Now, the problem set says we're doing 1 through 22 odd. Okay, so looking at number 2, and I have y prime is equal to 4y. And finding power series solution to the given equation. All right, so that's what we're going to do. First of all, I'm gonna look at it. I got a characteristic equation. R minus 4 is 0. So we know that y is equal to c e to the 4x is in fact the solution to this problem. Okay, but unfortunately this is chapter 3, and in chapter 3 that's not what we're looking for. We're looking for something different. So I've got summation n equal 1 to infinity and an x to the n minus 1 minus 4 times summation n equals 0 to infinity an x to the n is equal to 0. So I'm replacing the y and the first derivative of y with my series approximation. I'm then going to do a substitution. I'm going to say n is equal to n plus 1. And I'm doing that for two reasons. First reason, I want my x's to be the same indexing. And then it's convenient if my summation starts in the same spot too. And both of those things happen if I do that. So summation n is equal to 0. You see how I get a 0 there? I put an n plus 1 here, so I have n plus 1 equals 1. I subtract 1 from both sides, n is equal to 0. N plus 1, n plus 1, x to the n, minus summation, n equals 0 to infinity. I can bring that 4 inside. The constant can go in or outside of the summation sign, just like it can go in and outside the integral sign. 4an x to the n is equal to 0. I now combine in one summation. Summation n equals 0 to infinity. N plus 1, n plus 1, minus 4an, x to the n is equal to 0. I then say, I have a recurring formula. N plus 1 equals. So I set the guy inside the brackets equal to 0 for an divided by n plus 1. Okay, and then I say to myself, what is a0? Well, a0 is arbitrary. What if this were a second order differential equation? Well, then I would say a0 is arbitrary, and I'd say a1 is arbitrary. I have two constants of integrations, a1 and a0. I make them both arbitrary. Okay, that being the case, a1 has to be 4 a0 over 1. a2 has to be 4 a1 over 2, which is 16 a0 over 2, which is 8 a0. a3 has to be 4 times a2 divided by 3 what are we going to do about that? We're going to call that 64 a0 over 3 factorial. And then we got a4 is going to be 4 times 64 a0 over 3 factorial divided by 4. So we'll call that 256 a0 over 4 factorial. Do we have a pattern? Sometimes we don't necessarily have to look for a pattern. Well, this would be 2 to the 4th over 2, and this would be 2 to the 6th, right? And this is 2 to the 8th. So we could say a to the n is going to be 2 to the 2 raised to the n, a n over n factorial. So we could do that. There's a class in mathematics called combinatorics where you would do that. You'd find what it is. It's a 3-credit class. We don't really care. This is a differential equation class, so we might not do that. Anyway, back to where we are. We're saying that the answer to this equation is going to be A0, which was arbitrary, plus A1, which was 4A0 x, plus A2, which we will call 8A0, 8A0x squared, plus A3, what are we going to call that anyway? 32 over 3? 32 over 3 A0x cubed. All right. Now, originally we said that the answer to this problem has to be e to the 4x. Did we not? Yeah, that's what we said it was going to be, e to the 4x. All right, so what's the series expansion of e to the 4x? Well, it's going to be 1 plus 4x plus 4x squared over 2 plus 4x cubed over 3 factorial. Is that not what I have? Yes, that's what I have. So check, that's what I got. Okay.
What's it mean by arbitrary?
Arbitrary, an initial condition. When I do an integral f of x is equal to f of x plus c. What is c called? Constant of integration. It can be anything, right? We could call it arbitrary, right? So in a series approximation method, we call the A0, which is in fact that constant of integration, the initial condition of our problem that I don't know what it is, could be anything. Okay, so we call it arbitrary, and so that's what that means.
And then what does RF stand for?
Who? Recurring formula. So when I go RF, recurring formula. So when I have summation something x to the n, that something is 0, then that something, whatever it is, has to equal 0. And when I solve that something for a n plus 1 is equal to a n times something, there's things sitting there. So that would be my recurring formula where I get my coefficients. So that's how I'm getting my A's. My A0 is arbitrary, but that's where I'm getting my A1, my A2, my A3. Okay, I'm looking at number 4. And I've got y prime plus 2xy is equal to 0. If I was solving that in chapter 2, I would do it. I would say that dy over dx. I'd do it in chapter 1. dy over dx is equal to minus 2xy. And then I say dy over y is equal to minus 2x dx. And then I'd integrate both sides and say the natural log of y is equal to minus 2x squared plus some constant c. And then I'd go and say y is equal to e to the c e to the minus 2x squared. Okay, so if I was solving it not in chapter 3, that's how I would solve that problem. But I'm in chapter 3, so I can't do that. And I'm going to have y prime plus 2xy is equal to 0. Now, you notice it also says determine the radius of convergence for the recurring series. We're not going to do that. you'll do that in another math class, but in an elementary differential equation class, you don't need to do that. So back to what we're doing. I've got summation n equal 1 to infinity n a(n) x to the n minus 1 is equal to plus 2x summation n equals 0 to infinity a(n) x to the n is equal to 0. Right? So now I'm going to go and bring the 2x inside the summation sign. So n equal 1 to infinity n a(n) x to the n minus 1 plus summation n equal 0 to infinity 2 a(n) x to the n plus 1 is equal to 0. Okay, what are we going to do with that? Okay, well we'll do two substitutions. We're going to do a substitution in this one. N is equal to n plus 1, and we're going to do a substitution in this one. N is equal to n minus 1. And we're going to get summation n 0 to infinity n plus 1 a n plus 1 x to the n plus summation n equal 1 to infinity 2 a n minus 1 x to the n is equal to 0. Okay, now I'm gonna remove the n equals 0 guy out of here, and then I'm going to make one summation n equal 1 to infinity. So I'm going to remove the 0th guy. So it'd be a0 plus, because x to the 0 is 1, summation n equal 1 to infinity of n plus 1 a n plus 1 not x yet, plus 2 a n minus 1, everything times x to the n is equal to 0. Can a0 be arbitrary now? No.
How did you get to a0?
Oh, in the summation guy, at n is equal to 0, I have 1. Oh, that's a1. Good point. There, that's better.
You just put 0 into that summation formula?
Yeah, I put a 0 in there. So I got it. The 0th term would be 1 plus a times a1 times a to the 0, which is 1, which is just a1. All right. So what do I know? Well, I know that a0 is going to be arbitrary. I also know that a1 is going to be 0, because a1 is sitting out here by itself and with no x term associated with it, so it has to be 0. I also know that from my recurring formula, so I've got a recurring formula sitting in there, that a n plus 1 is going to be equal to minus 2 a n minus 1 divided by n plus 1, and that this is true for all n greater than or equal to 1. Okay, because the summation starts at n equal to 1, the recurring formula has to start at n equal to 1. Okay, so I know a0 is arbitrary, a1 is 0. I know that a2 is going to be n is equal to 1, that's going to be minus 2 A0 over n is equal to 1 over 1. So A2 is going to be minus 2A0. A3 is going to be minus 2. N is now 2. A1 divided by 2 divided by 3. Let's come back to this guy. N is 1. That's a 2. So that's just a minus A. Okay. Divided by what? Divided by 3. But A1 is 0, so this guy is 0. This strongly implies that for all odd n, wrong n, misspelled n. For all odd n, an is equal to 0. Because every time I get an odd n, I'm going to get an odd guy up here, and he's going to be 0, and it's just going to go away. So now I look at A4 minus 2 times n is a 3 times A2. A2, and A2 is minus A0, so this is going to be 2A0. I'm going to look at A6 because A5 is 0, minus 2. Oh, I blew that, didn't I? I still have to divide by 4. Divide by 4. Divide by 4. So this is going to be A0 over 2. Now, A6 is going to be minus 2. A0 over 2 divided by 6. Oh, let's see, what is that? All right, the 2 and the 2 goes away. That's going to be minus A0 over 3 factorial. I'm going to do another one. A8 minus 2 times A0 over 3 factorial divided by 8, which is going to be minus, that's a minus, so this is a plus, A0 over 4 factorial. All right. Now we're going to check our work. Y is A0 minus A0x squared plus A0 over 2x to the 4th minus A0x to the 6th over 3 factorial plus A0x to the 8th over 4 factorial. Y prime is going to be, that guy goes away, minus 2A0x plus 2A0x cubed minus the 6 goes out in front, minus A0x to the 5th plus the 8 goes out in front, A0x to the 7th over 3. And then I'm going to say, well, what am I doing? I want one of those guys, and I want 2x of this guy. All right, so 2xa0 minus 2xa0 goes away. I got 2 minus 2a0x cubed plus 2a0x cubed. They go away. I've got a0x to the 5th, a minus a0x to the 5th. I've got a0 minus a0 x to the 7th over 3 plus a0x to the 7 over 3. 0 is equal to 0, that checks. So that's the way I'm going to check my work. I'm going to take the series expansion, I'm going to find all the derivatives I need to find, I'm going to multiply them by whatever their coefficients were, and see if I get what I'm supposed to get. Okay, I'm looking at number 6. X minus 2 y prime plus y is 0. Okay, we still have a way to solve that if we really wanted to. Series expansion. X minus 2 summation n equal 1 to infinity n an x to the n minus 1 plus summation n equals 0 to infinity a n x to the n is equal to 0. Okay, I've got summation n equal 1 to infinity n a n x to the n minus summation n equal 1 to infinity 2 n a n x to the n minus 1 plus summation n equals 0 to infinity a n x to the n equals 0. I'm going to do a substitution in this guy, n equals n plus 1, so that I get the same exponent on all my x terms. Okay, so I've got summation n 1 to infinity n a n x to the n. Remember to always start at the top of your paper when you're solving a problem like this, and you may want to go get some legal paper so you don't run out of room. Minus summation n equals 0 to infinity 2n plus 1 a n plus 1 x to the n plus summation n equals 0 to infinity a n x to the n equals 0. Okay, I'm going to take the n equal to 0 term out of this guy, the n equals 0 term out of that guy, and then that'll let me have summation n equal 1 to infinity. So that's the plan. Okay, I take the n equals 0 term out of here and I get 2a1 times x to the 0 plus a0 times x to the 0 plus summation n equal 1 to infinity. I have n a n minus 2 n plus 1 a n plus 1 plus a n, everything times x to the n, is equal to 0. Okay, I have a situation. The situation is that 2a1 plus a0 has to be 0. Okay, so a0 is arbitrary, and a1 is equal to a0 over 2. So the a0 goes on the other side of the equation. a1 is equal to minus a0 over 2. I have a recurring formula. Recurring formula. A n plus 1 equals. Okay, I'm going to put that on the other side of the equation for minus, that on the other side of the equation for a minus, and then I'm going to divide by a minus, making the minuses go away. So I'm going to have a n plus 1 a n divided by 2 n plus 1, which is a n over 2. Okay, so now I know a0 is arbitrary, a1 is minus a0 over 2. and this is for all n greater than or equal to 1, because my indexing starts at 1. All right, so A2 is equal to minus A0 over 2 divided by 2, which is minus A0 over 4. A3 is minus A0 over 4 divided by 2, which is minus A0 over 8. And AN is going to be minus A0 over 2 to the n. Okay, so I have lots and lots of them. All right, so I end up with y is equal to A0 minus A0 over 2x minus A0 over 4x squared minus A0 over 8x cubed minus A0 over 16 x to the 4th plus blah blah blah, lots of them. Y prime is going to be minus A0 over 2 minus A0 over 2x minus A0 over 4x squared minus A0 over, boy did I ever mess that one up. Did I mess that one up? I guess not. No one called me on it, so it must be okay. All right, so this is, I got that one, I got this one. Minus 3 A0 over 8 x squared minus A0 over 4 x cubed. Okay, now I need two of these prime guys when I figure out what it is I've got, because that's just the nature of the beast. So I'm going to write it down twice. And this is problem number 6. Problem number 6. So I need x of these guys. I need minus 2 of those guys. And I need 1 of these guys. And when I get done, I best have 0. And if I don't have 0, I better come up with a good reason. Okay, so I've got plus A0 minus A0. Those two guys go away. Okay, I've got minus A0 over 2 minus A0 over 2 for minus A0, and then I have x, and then I got a plus A0x. Those guys go away. I've got a minus A0 over 4 a x squared minus A0 over 4x squared minus a half A0 x squared, and then I've got minus 3, I got 2, I got positive 2/8. Those guys go away. I got minus an 1/8, minus another, minus a half, minus a half, plus a half. I got minus an 1/8 plus a half for plus 3/8 A0x cubed, and then I got minus A0x cubed. Those guys go away. So my I check. I can't check past the where I am, because I need another derivative to go by that. Go any further out. I need another term in my equation. So that guy checks.
Well, can you go back up a little bit?
Yeah.
Oh,
Higher.
all right.
all the way up to there.
How did you, from where the green line is, how did you get to the black line?
From here to there. Okay, I took off the n is equal to 0 term from that summation.
Oh, that's how you get the 2A1.
2A1.
Okay.
I took out the n is equal to 0 guy here. A0.
Okay.
Plus summation n equal 1 to infinity of that coefficient minus that coefficient plus this guy, the whole thing x to the n. Yeah. And and I don't have the option of making a mistake, right? You make a mistake doing this, and there's no recovery. You know, you can't come back. You can't, after you do something wrong, the only thing you can do is wad up the paper and start at the beginning again. Well, maybe you can find it and correct it. It's not too far away. Okay, we'll do number 12 next. 12 says, use the method to find two linearly independent power series, determine. All right, so we're going to do that, but we're not going to determine radius of convergence. So I have y double prime is equal to 4y. Okay, so I've got y double prime minus 4y is equal to 0. So that's what I'm solving. So I've got summation n equal 2 to infinity n minus 1 a n x to the n minus 2 minus 4 summation n equals 0 to infinity a n x to the n is equal to 0. I'm going to do a substitution. N equals n plus 1, n plus 2. I'm doing that so that this becomes x to the n, and I can combine my summation signs. That's why I'm doing that. So I got summation n equals 0 to infinity, n plus 2, n plus 1, a to the n plus 2, x to the n, minus summation n equals 0 to infinity, a n x to the n is equal to 0. Okay, I'm going to combine those two summations. Summation n equals 0 to infinity, n plus 2, n plus 1, n plus 2 minus a n x to the n is equal to 0. So I'm doing a substitution. N equals n plus 2. I put n plus 2 is equal to 2. I get n is equal to 0. I put an n plus 2 there. I get an n plus 2. N plus 2 minus 1, n plus 1. N plus 2 for the n plus 2. N plus 2 minus 2 is an n. What was your question?
You just answered it.
Yes, I know I did. Did I make you feel bad answering it?
No.
No, didn't? Okay.
You asked a question.
All right. Well, I don't have anything over here to throw or anything, so it's hard. Well, I got this book, The Richest Man in Babylon, so I could throw it, but it's not big enough, and I probably wouldn't make it that far. So, all right. So now I got a recurring formula. And it says a n plus 2 is equal to a n divided by n plus 2 times n plus 1. Okay, and this is for all n greater than or equal to 0. So I have to start at n equal to 0. Okay, that being the case. So I have a0 and a1 are both arbitrary. Okay, so that means I could have two solutions here. So I'm going to have case 1. A0 is arbitrary. A1 is 0. So So that'd be case 1. And I'd say, well, in that case, A2 would be A0 divided by 2. That's my original formula anyway. Minus 2. Alright. That's alright. I'm just checking to see if I made a mistake. Alright, A3 is 0. A4 is A2 over 4 times 3, which is going to be A0 over 4 factorial. A5 is going to be 0. A6 is going to be A0 over 6 factorial. Okay, and then we're going to look at our second case, case 2. A1 is arbitrary. If I could spell arbitrary. And A0 is going to be 0. Okay, so in that case A0 is 0. A1 is arbitrary. A2 is 0 because A0 is 0. A3 is going to be A1 divided by what? 3, this is a 1, so that'd be 3 times 2, 3 factorial. A4 is 0. A5 is going to be A1 divided by 5 factorial. Alright, so I have two solutions. I have solution Y1, which is going to be A0, where'd it go? A0 plus A0 over 2 x squared plus A0 over 4 factorial x to the 4th plus A0 over 6 factorial x to the 6th, and I have another answer y2, which is going to be A1 plus A0 over 3 factorial ax cubed plus A1 over 5 factorial x to the 5th plus A1 7 factorial x to the 7th plus blah 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 plus blah blah blah. Those look like cosine functions, don't they? No, they don't. Those look like hyperbolic sine, hyperbolic cosine functions, don't they? That's what they look like. So this looks like y1 looks like A0 hyperbolic cosine x, and this looks like A1 hyperbolic sine x. So that begs the issue of where did I mess up? Huh? Right? Because I had to make a mistake. That can't be the right answer. See this 4 sitting right here? You notice that it doesn't occur there. You notice that? Is that professionally embarrassing or what? And so there's a 4 sitting right there, right? And there's a 4 sitting right there, right? So that makes all this total BS down here, right? Alright, so we'll get the big eraser and do it again. There's nothing wrong with the other part, but if you have the wrong recurring formula, you're going to get the wrong answer. That was obvious to the casual observer that something was wrong, right? You did notice that, correct? You did notice that? All right, so case 1, A0 is arbitrary, A1 is 0. A2 is going to be 4A0 divided by 2, which is going to be 2A0. And A3 is 0. A4 is going to be 4 times 2A0 divided by 4 factorial. Oh, that's going to be A0 over 3. A0 over 3. Then A3 is 0. A5 is 0. A6 is going to be 4 A0 over 3 divided by 6 factorial. We'll just leave it that way. Yeah, that's pretty big. Oh, way to go. Too big of an eraser. A0 over 3, 6 factorial. Okay, so we're going to look at the other guy. And the other guy is A0 is 0. A1 is arbitrary. A2 is 0. A3 is going to be 4A1 divided by 3 times 2. 3 times 2. 2A1 over 3. Interesting. A2, that's a 2, that's, well, I guess so. All right, A4 is 0. A5, 2A1 over 3 times 5 times 4. 4A0 over 5 factorial. A1, right. 4A1 over 5 factorial. A6 is 0. A7, 4A4 times A0 over 5 factorial divided by 7 times 6. So A7 is going to be 16 A0 over 7 factorial. Now, why don't we have such nice things happening over here, I wonder? A2, 4A0 over 2, that's right. A4, this is going to be 4A2, not divided by 4 factorial, but divided by 4 times 3, right? Divided by 4 times 3. All right, so this becomes 16 A0 over 4 factorial. Okay, and this guy here is wrong. So it's going to be 4 times 16 A0 over 4 factorial divided by 6 times 5, which is 64. 64 A0 over 6 factorial. Why isn't this getting any bigger? Well, because I'm hosed. That's a 4. So this is a 4 over 3 factorial. This is a 4 times 4a1 over 3 factorial times 5 times 4. So this is 16 a1 over 5 factorial. And this is going to be is going to be 16a1, so this is going to be 64a1. Okay. Now I'm happy. How many times did I have to do it over? Too many. Yeah, I agree. That's a good answer. Okay, so case 1, y1 is going to be a0 plus 2a0 x squared plus 16a0 x to the 4th over 4 factorial plus 64x to the 6th over 6 factorial a0. All right, that's one of our answers. We're going to check our work. y1 prime, he goes away, 4a0x plus 16a0x cubed over 3 factorial plus 64a0x to the 5th over 5 factorial, y1 double prime, 4a0 plus 16a0x squared over 2 factorial plus 64a0x to the 4th over 4 factorial. And I want, what do I want? I want one of these guys and minus 4 of those guys to be 0. That's what I want. All right, so I got minus 4 plus 4, minus 8 plus 8, minus 16, no, minus what? Minus 64 plus 64. Boom, boom. So 0 is equal to 0 and it checks. So my y1 term checks. My y2 term is going to check. I have two independent solutions. I could put them together. Right? There'd be nothing wrong with putting them together with both a1s and a2s. I could do that too. Okay. I'm going to look at 16. Show that the power series solution fails for these. Okay, so number 16, we should show that it fails. So if we get an answer, then that's not good. 2xy prime is equal to y. Now, just because it fails doesn't mean that we're not going to find another section in the book where we're going to figure out how to solve it. We will, okay, with a series approximation. But with the series approximation we're currently using, we can't do it. Well, is there anything wrong with a series approximation that goes summation an x to the n over 2, for example? Nothing wrong with that, right? I could have one that does that. But I'm not using them now. I'm using only coefficients that are exponents that are whole numbers, and in that case I may have a situation where I can't solve a problem. This is supposed to come up that way. Okay, so I've got 2x summation n equal 1 to infinity n a n x to the n minus 1 minus summation n equals 0 to infinity a n x to the n equals 0. I got summation n equal 1 to infinity 2 n a n x to the n minus summation n equals 0 to infinity a n x to the n is equal to 0. Okay, I'm going to take, that's an n there in case anybody's wondering. I'm going to take the n equal to 0 term out of this guy. So I'm going to take him out and have minus a0. And then I'm going to have plus summation equal 1 to infinity of 2n a_n minus a_n x to the n is equal to 0. Okay, well, that being the case, minus a0 has to be 0. I don't have a choice. And my recurring formula becomes an is equal to 0. Yeah, that's basically it. No. Yeah, it's been, my recurring formula becomes 2n minus 1 times an is equal to 0. an is equal to 0. So the method fails. I don't have any coefficients. What a bummer.
How'd you get the 2n minus 1? How'd you get the 2n minus 1?
2n minus, well, here's 2n. There's minus 1. There's my a0. I factored out the an.
Isn't that supposed to be a 2x?
No. The x came in and added to the n minus 1 to just be x to the n. So when I brought the 2x inside the summation, I keep the 2, but I multiply the x times n minus 1, it becomes x to the n. I added the exponents in the x and put them together. Was that sneaky and devious? Oh, was it sneaky or was it just devious? Or was it both sneaky and devious? Oh, okay, whatever. But there is a case where I can't have a solution. Okay, well, let's see. What are we going to do next? We're going to do number 20. Number 20. Y double prime minus 4y equals 0. And we're going to have y at 0 is 2, y prime at 0 is 0. Now what does y at 0 mean? That means a0 is 2. What does y prime at 0 is 0? What does that mean? That means y1 is 0, right? This y guy is a0 plus a1x plus a2x squared plus a3x cubed plus blah, 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 blah. Y at 0 has to be a0, which is set at 2. So when I'm given an initial condition, a0 ceases to be arbitrary. I know what it is. When I take the derivative of this guy, I get a1 plus 2a2x plus 3a3x squared plus blah, 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 blah. And when I look at y prime at 0, that's 0, everybody else is 0. That's A1, which in this case is set to 0. So A1 is going to be 0, and A0 is going to be 2 by the initial conditions that I'm given. Okay, so now we're going to solve our problem. Y double prime minus 4y is 0. And so I've got summation n equals 0 to n equal 2 to infinity, n minus 1, an x to the n minus 2 minus summation n equals 0 to infinity 4 an x to the n is equal to 0. I'm going to do a substitution. N equals n plus 2 so that I get both my x's raised to the same exponent, which would be convenient. Summation n equals 0 to infinity, n plus 2, n plus 1, an plus 2, x to the n minus summation n equals 0 to infinity, 4 an x to the n equals 0. Okay, my indexes come together, so I can put that all under one summation sign. Summation n equals 0 to infinity, n plus 2, n plus 1, n plus 2 minus 4 an x to the n is equal to 0. I have a recurring formula. N plus 2 is equal to 4 an divided by n plus 2, n plus 1. I also know that A0 is 2 and that A1 is 0, and that this is for all n greater than or equal to 0. So I start at n is equal to 0 to give me A2. So A2 is going to be 4 A0, which is 2, divided by 2 times 1, making that 4. A3 is going to be 0. So A3 is 0. And in fact, all an is 0 for n odd. And so A4 is 4 times A2 divided by 4 times 3, which is 4 over 3. Okay, A5 is 0. A6 is 4 times 4 over 3 divided by 6 times 5. Okay, so if I got a 3 I can bring down. I need a 4 and a 2. So if I'm going to make this, no, I don't have anything. I got 16 over 30, 90. 16 over 90. Is that what I have? Okay, A5 is 0. A7 is 0. A8, 4 times 16 over 90 times 8 times 7. Time to get out your calculator. 4 times 16 divided by 90 divided by 8 divided by 7. Change to a fraction. So that's going to be 4 over 315. Okay, so I'm saying, all things being equal, that y of x is equal to 2 plus 4x squared plus 4/3 x to the 4th plus 1690s x to the 6th plus 4 3/15 x to the 8. Okay, I'm checking my initial condition. Y at 0 is supposed to be 2. It is 2. Check. My initial condition is right. Okay, now I'm going to take the first derivative, y prime, and I'm going to get 8x plus 16 over 3x cubed plus, I don't know, 16 times 6 divided by 90, change to a fraction, 16/15 x to the 5th plus 4 times 8 divided by 3/15, change to a fraction, 32. Well, that was good. I could have done that in my head. X to the 7th. I'm going to check my initial condition. Y prime at 0 is supposed to be 0. It is 0. Check. So my initial conditions work. I'm now going to go y double prime, 8 minus 16x squared plus 16x squared plus 16 over 3x to the 4th plus, let's see, 3/15 divided by 7, 45. 32 over 45 x to the 6th. Now, I'm supposed to have one of these guys and minus 4 of those guys. Okay, and if I do, they go away. And if I do, they go away. And if I do, he goes away. And if I do, they go away. So it looks like I'm going to check. 0 is equal to 0. Check. Okay. Well, with that, we've managed to make it all the way to the bottom of the problem set, which only went to 21. And I went to 20, so I guess we need to quit for the day. So does that look like fun? Does not look like something you haven't done before ever in your life?